Welcome to my Implicit Differentiation podcast, part 1. We did this problem in class. We found the horizontal tangent lines, and we found that they were at x equals -4. And you were all thinking, well, if it's a horizontal line, shouldn't it be going through the y-axis? That's just the x location. We have to find the y location. All right, so this will be at a point, not necessarily through the y-axis. So how we find the rest of the point is we plug it back into the original equation. And actually, this was a really easy equation to solve. So I plugged in -4 because we had x equals -4 when we set our numerator equal to 0 because a fraction will be equal to 0 wherever the numerator is 0. So when we plugged in -4, I got 400 plus 16y squared minus 800 minus 160y plus 400 equals 0. Well, all the constants canceled out, and I'm left with 16y squared minus 160y equals 0. Factor out the greatest common factor, 16y, and you've got 16y times y minus 10. Put this, by the way, in your notes along with that, so you can see the steps for the whole problem, so you'll know exactly what to do. So if I set 16y and y minus 10 equal to 0, that's the y coordinate. So there's two places. Right? So when x was -4, y was both 0 and y was 10. So that means I have two places where I have a horizontal tangent line. There's one at -4, 0, and there's another one at -4, 10. Okay? But they both have the same x value. Okay? So those are the two locations, and we found the horizontal tangent lines. Let's find the vertical tangent lines. So pause the tape if you need to, because I kind of wanted to just have the work up here. I figured I could talk about it. I think it was certainly easy enough for you to figure out my work here. And we're going to look at the vertical tangent lines, and then we're going to look at the graph of this, right? And I think it would be a good idea for you actually to put the steps in how to change this into a form you can graph, and then do the graph along with me. Right? I didn't graph it yet. I did do the work to change it, but you'll be able to follow along, and I'll go step by step through that. All right? So come meet me on the next page where we're going to find the vertical tangent lines. All right, so we set our denominator equal to 0, 16y minus 80 was the denominator, and we found y equals 5 was where we had the vertical tangent lines. And we need to find the x values, right? So we had to substitute 5 for y into the original equation and solve for x, and it was no more difficult than the other one was. So I plugged in, so I have 25 times x squared plus 16 times 5 squared plus 200x minus 160 times 5 plus 400 equals 0, gives me 25x squared plus 400 plus 200x minus 800 plus 400 equals 0. And so I'm left with 25x squared plus 200x equals 0. Factor out the greatest common factor, 25x. And so you have vertical tangent lines at 0, 5. Lost a parentheses there. And 8, 5, right? Because x here was 0 and x is, -8. X is -8. Right? So that's where we have some vertical tangent lines. We have two places with vertical tangent lines, both with horizontal tangent lines. Notice that the y values, the vertical tangent lines had the y values in common, and the horizontal tangent lines had the x values in common. Okay? And that's just because there were x's in the numerator and there were y's in the denominator. All right, so we had to solve for x in the to find the horizontal tangent lines, and we had to solve for y to find the vertical tangent lines, because that just happened to be what was in each portion of that fraction. All right, so now let's go to the next page. And oh, by the way, so let me go back to this page one more time. So 25x squared plus 16y squared plus 200x minus 160y plus 400 equals 0 could be what kind of conic? Well, x squared and y squared are both positive, so it is not a hyperbola. Both x and y are squared. It is not a parabola. That leaves circle and ellipse. How you can tell which one it is? If there were no coefficients in front of, or there were the same, either there were no coefficients or the exact same coefficient in front of x squared and y squared, this would have been a circle. We've got different coefficients in front of x squared and y squared, which means that the horizontal and vertical distances are not the same. This was an ellipse. All right, and all it is a little completing the square. Really no different than my geometry class does, except you'd have one extra step here. All right, so I didn't have a coordinate plane handy, so I hope you don't mind. I just made the background a grid paper and put a little axes on it, and that way I didn't have to go and cut and paste a copy of a coordinate plane in here. Very clever of me, wasn't it? All right, and I think you can still read it over the. I think I tried to make it light enough so you could still read my writing over it. All right, so here's the original equation: 25x squared plus 16y squared plus 200x minus 160y plus 400 equals 0. We move the constant out of the way because we only want the x's and the y's, not that constant term. All right, so now I need to factor out the a value, the coefficient in front of x squared, out of all of those two terms. And so I had an x squared and an 8x. I kind of saved myself a step because we're going to be doing completing the square. Right? I already added in the b divided by 2 squared in there. All right. So if you wanted to do it as 2 steps, it'd be you would have just factored out the 25 out of the x squared and the 8x, and then I just added this portion here. So I did 2 steps in one. I factored out the 25. And then I added what made that a perfect square, b divided by 2 squared. I factored out the 16, and just to save myself a little time, I added the b divided by 2 squared over there. And for some reason, I didn't bother to write it into the next step, but I should have written it as soon as I wrote it in. So up here, I should have also had, technically, because at one spot I don't balance, 25 times 8 divided by 2 squared, and a 16 times negative 10 divided by 2 squared. All right, so maybe if I move everybody over just a teeny bit, everybody just scrunchie together. Oops, forgot the plus sign there. So I didn't really add b divided by 2 squared. Oh, well, there goes all my numbers. Now they're all, look at that. They're all in pieces. What are the chances I'll move this all over at the same time? Isn't that ridiculous? All right. There we go, and I don't know what that mess is. There's a parentheses. It does not want to move. I give up on that section there. I'll just rewrite it while you're writing down the rest of these steps. So I didn't really add in, it was 16 times negative 10 divided by 2 squared. I didn't really add in an 8 divided by 2, which is 16. And I really didn't add in a negative 10 divided by 2 squared, which is 25, because we had coefficients that we pulled out. So in front of the parentheses, there's a 25. So when I add it to the other side, that's really 25 times 16, and that's really 16 times 25. All right, so I have to make sure that I don't forget that outside those parentheses are these coefficients. All right, so now I just simplified. 8 divided by 2 squared is 16. Negative 10 divided by 2 squared is 25. And factored, all right, x squared plus 8x plus 16 is just x plus 4 squared. Y squared minus 10y plus 25 is y minus 5 squared. And that, when we add it together, equals 400. All right, when it's in standard form, we want to have that equal to 1. And that is going to give us the values of our horizontal and our vertical axes there. All right, so we just divide everything by 400. It always goes in evenly. Never seen it not go in evenly. All right, and so that's going to reduce to 16 and 25, which are perfect squares, right? So that means that, see, if this was a circle and 16 was my radius, right? That means, excuse me, 16, it was equal to 16. That would mean 4 is the radius. So technically, one of my radii is 4. So I'm just going to call this radius 1. I like to think of it that way. It's not truly a radius because it's not a circle, but it's kind of like a radius. And this is radius number 2. And he's that square root 5. So if this were a circle and we had equals 16, our radius would be 4. And if this were a circle and it was equals 25, the radius would be 5. And so it kind of is 4 and 5, but it's two different distances because this is not a circle and it's not going to be symmetric along the x. It's not going to be the same distance along the x and the y. So let's graph this. The center is at negative 4, 5. So, I'm running out of space only because I can't pull my microphone cord any farther. 1, 2, 3, 4, 1, 2, 3, 4, 5. Right there. And then the horizontal distance is 4, 1, 2, 3, 4 to the right, and 1, 2, 3, 4 to the left. And the, oops. Did I say 4? Oh, shame on me. Negative 4. Negative 4. I put 4 into negative 4. That's okay. 1, 2, 3, 4. It's like I looked too quickly. I looked over at the y and saw the minus, and just imagined I saw a minus by the 4, and it was a plus. And we know the sign's the opposite. So 1, 2, 3, 4. There we go. It's all good. It's in the right spot now. All right, and that is the negative 4, 5 is our center. We're centered there. And now the vertical axis is 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So there's what it looks like. Assuming I made no other sign errors besides that one I just made an instant ago. Let's find out where those vertical and horizontal tangent lines were. They were at 0, 5 and negative 8, 5. Right, so 0 on the x, I'm going to draw in another color, green. And so 0, 5. Notice right there at 0, 5, we have a vertical tangent line. And right here at negative 8, 5, we have a vertical tangent line. Well, that makes a lot of sense that the edges there would be a vertical tangent. And sorry, that is not a perfectly well-drawn ellipse, but that is the best you're going to get me to draw. So I gave it my best shot on the drawing there. And I don't have a compass that does ellipses. And the horizontal tangent lines were at negative 4, 0 and negative 4, 10. Right? Come on, graph. There we go. Right here at negative 4, 0 and at negative 4, 10. So I thought this was a good idea for me to graph this for you. A, because I think you could use a little practice in factoring and rewriting conic sections. B, because you can also use a little practice in graphing them. And C, I think it helps this whole problem make sense when you can see the graph and you can see the vertical and horizontal tangent lines. So if it's something you can easily graph, and not everything will be something you can easily graph, it's not a bad idea if you want to check it. And some of them you can also graph it on a graphing calculator, but I think it's also very worthwhile on this problem to be able to graph this one by hand. I think it might be a test question sometime, just a hint. All right, so here's this problem here. Let's move on and do a little bit more implicit differentiation. We spent a whole lot of time with algebra there. All right, so here's one that's in, I believe is in your notes. I left it up here because it's so nicely written, not by me, because it's typed. Only once in a blue moon do I type on the smartboard. 2y equals x squared plus sine y. Can't be solved for y. There's absolutely no way you can pull the y out of sine. All right, it is trapped in there. If it weren't sine y, then you might have been able to solve for it because you could always divide y by 2. So we have to use implicit differentiation. We take the derivative of the 2y, we take the derivative of the x squared, we take the derivative of the sine y. And note that dx in the denominator means it's the derivative with respect to x. So only the x squared is not a chain rule. All the other two are a chain rule. Right? So the derivative of 2y is 2 dy dx. Derivative of x squared is 2x. Derivative of sine y is cosine y dy dx, because the derivative of the y part is dy dx. Right? That one was all the y ones are chain rules. All right, so now we want to get the things with dy's together and the things without dy's on the other side. So we just subtracted the 2x and we subtracted the cosine y dy dx, and we factored out dy dx, and we're left with 2 minus cosine y equals 2x. Just divide both sides by 2 minus cosine y, and we have our derivative. Dy dx is 2x divided by 2 minus cosine y. So really, other than remembering that it's a chain rule every time you see a y, really it's just a little bit of algebra thrown in with our differentiation as we're isolating. Let's do a few more problems. Some of these may be completely in your notes and some of them I'll do with you. I think I had the steps already twice. So I'm just going to go right past it because we've run on over that. Find the equation of the tangent line, the normal line to the curve x squared minus xy plus y squared equals 7 at negative 1, 2. I have no idea why there's a random little mark there. Get rid of it. All right, so, oh, I know what it is. Don't forget to distribute the negative. Actually, I'll put that negative. That's why I underlined the subtraction sign, so we wouldn't forget. All right, so that's, and then we use parentheses, so we wouldn't possibly forget, okay? If it's just a plus, you're never thinking about it, but if there's a negative, you've got to remember to distribute it because you're going to have plus something on the product rule. All right, so that one's the product rule. We've seen x times y's derivative quite a few times, and so we have derivative of x squared is 2x minus the whole quantity of x dy dx, the first times the derivative of the second, plus the second times the derivative of the first, plus y. And then the derivative of y squared is 2y dy dx, derivative of 7 is 0. All right, we'll distribute the negative to both of those terms. We can drop those parentheses, 2x minus x dy dx, minus y plus 2y dy dx is 0. We're going to subtract the 2x as the only thing that is in the wrong side. Subtract the 2x from both sides. Factor out the dy dx. We have 2y minus x dy dx equals y minus 2x. If you were any way confused about the derivative of that product xy there, I also put it at the bottom of your page. All right, and so we just divide both sides by 2y minus x, and our derivative is y minus 2x divided by 2y minus x. No reducing there. And so we were asked to find the tangent line and normal line. You just need to find the slope and write the equations. So we plug in a negative 1 everywhere we see an x and a 2 everywhere we see a y. We get 4/5 as the slope. The normal line, just flip it and make it the opposite, negative 5/4. And I don't think anyone has any trouble writing the equation of a line in point slope form. And it's fine to leave it. Just know that if it's a multiple choice, it might be rewritten into slope intercept form, or it might just be y equals and that 2 is moved over. All right, so just be aware that it could be written in different forms. However, any form you use is a proper form in this class and on the AP test. I think we can do another one because I'm only at 18 minutes. Oh, here's the tangent lines again. And here they are in slope-intercept form, just in case you had any issues on how to write those in slope-intercept form. You just distribute the 4/5, and 2 is the same as 10/5, and you add it together. And you distribute the negative 5/4, and you add in 8/4, and so that gives you 3/4. There we go. Okay, so it's in standard slope-intercept form. All right, so a new symbol. Look at that. We have the second derivative. I don't know how many of those problems I have in here, but I think I have a couple. And is this the same problem twice? No. I'm just going to do one now, and then we'll pick up with this problem. We'll pick up with a new problem in class. So I'll do one time. All right. So you have been introduced to the second derivative, and I can do this problem without hearing anyone whine. All right. So we want to find the second derivative. To find the second derivative, what do you got to do first? Find the first derivative. So first step number 1 is find dy dx. All right, so we have, and that's not a very difficult derivative to take. Derivative of 2x cubed is 6x squared. Derivative of 3y squared is going to be negative 6y dy dx, and that would equal 0. We got to move the 6x squared, so we have negative 6y dy dx equals negative 6x squared, and then divide both sides by negative 6y. Right, so that's going to give us dy dx equals, that of course will reduce, the negatives reduce, the 6 reduces, and this is going to be x squared divided by y. Now we're going to take the derivative of that. So now we'll take the derivative with respect to x of dy dx. All right, so the derivative of dy dx with respect to x is, and actually, no, I'm going to switch colors right now just so you can see that, so that it's color coded when I go from the first derivative to the second derivative. All right, so we have d2y dx2, that just means second derivative equals. So notice our second derivative is already isolated, and you might think, oh, all I got to do is take the derivative. Yes, but you might have a little simplifying to do. This, by the way, is a quotient rule. Yes, if you said quotient rule, you were correct. All right, so we have a quotient rule over here. All right, so u is x squared, du is 2x, v is y, dv is dy dx. So it's going to be equal to the denominator, y, times the derivative of the numerator, which is 2x, minus the numerator, x squared, times the derivative of the denominator, which is dy dx, divided by, I got everybody right? Yep. All right, and divided by our denominator squared, y squared. Now we need to simplify that. So we have d2y dx2 equals, that's going to be 2xy minus x squared. What do we do with the dy dx? We've already got it solved. We can't leave a dy dx in there. Absolutely not can we leave a dy dx in there. But we know what dy dx is because we found it. So on these problems, you are going to need to substitute for dy dx. Oops. My D didn't come up. That's a D, not an A. It's not dyx. All right, so we're going to just replace that dy dx with an x2y. x2 divided by y. And in the denominator, we have a y squared. Oh, and look at that, a complex fraction. I'm starting to run out of a space a little bit here. So I'm not going to do this as a second step. I'm just going to pluck what I need to right next to it. And what we're going to need to do is multiply. You've got one denominator you need to get rid of, and one denominator only. The one that matters is the one that's making this a complex fraction. The denominator nobody cares about because there's only one single value there. There's not a fraction in your denominator. There's just a fraction in your numerator. So multiply all terms by y, right? Because we have to distribute to everybody in the numerator, and there is only one thing in the denominator. So I'm going to just put a little y right next to everybody. You get a y, and you get a y. So that's this step right there. All right, and so now this will cancel out the y. Oh, so excuse me. And you get a y. All right, so I've multiplied the numerator by y. There's two terms, so it has to be distributed. And I multiply the denominator by y. And I think we can fit the last line in here, and that is just simplifying. Where am I going to go? If I just extend the page just a little bit, and then I'll scroll up. I think if I moved everybody up, I think I wrote too big. T2y dx squared equals, this would be 2xy squared minus x to the fourth all over y cubed. And that's our second derivative. That wasn't that bad. And I'm going to move this over, and it's staying together. There's our second derivative. And let me scroll up this page. My box is just a wee bit too small. And unfortunately, I can't go to full screen because otherwise I can't record. So let's see if we got everybody in here, because you may be behind in writing things down. Maybe you were trying to listen and the page is not being very hospitable. Come on, there we go. Oh, we almost fit everybody in. All right, if we just move things up a little bit. Oh, actually, if we move the page up to the top of the page, I think we can get everybody in there. All right, so ignore that. It's the next problem. And we'll just move everybody up. So you see, we take the first derivative, and then you just take the second derivative. By the way, because you have dy dx isolated, your second derivative is already isolated. d2y dx2 is already isolated for you. It's just that you're going to have a dy dx kind of stuck in the middle of your problem, and you'll have to just do a substitution, and you'll know what dy dx is because, well, to take the second derivative, you had to find the first derivative. And you'll just simplify it because you're going to end up with, most likely, a complex fraction. Not always, but 99.9% of the time. And there we go. There's this problem. So tomorrow in class, we're going to do more of these. Actually, it depends which day you're watching this, but on Monday in class, we're going to do more of these, more second derivatives. And really, they're not so bad at all, as you can see. All right, thanks for watching the tape. Bye.